there is a simpler alternative form of the equilibrium carrier concentrations N and P that you will encounter in device analysis. Recalling that EI, the Fermi level for an intrinsic semiconductor, lies closely to the mid-gap. So we can apply the simplified closed-form expressions obtained from the last video to an intrinsic semiconductor. In the intrinsic semiconductor, N equals P equals Ni, and EI equals EF. So we can obtain Ni from two expressions. Then we will solve Nc and Nv with these two equations. Finally, substitute Nc and Nv back to the closed form expression, and then we obtain N and P. These two expressions are valid for any semiconductor in equilibrium state whose doping is such as to give rise to a non-degenerate positioning of the Fermi level. In this expression, only one constant Ni and two energy levels EF and EI are involved. This form is also much easier to remember because we just need to reverse the position of EF and EI to get N and P. As seen from the last slide, the intrinsic carrier concentration Ni are commonly used in the evaluation of the carrier concentrations N and P. We can get even further relationships involving this important material parameter Ni. We can multiply the corresponding size of these two Ni expressions and obtain the Ni expression in terms of Nc, Nv, and energy band gap, Eg. This expression shows Ni as a function of known quantities and may be used to compute Ni at a specified temperature or as a function of temperature. This plot shows Ni as functions of temperature in silicon, germanium, and gallium arsenide. Here is another very important Ni relationship. We multiply the corresponding size of N and P expression, and then we get the result N times P equals Ni squared. This result looks trivial, but the NP product relationship often proves to be extremely useful in practical computations. If one of the carrier concentration is known, the remaining carrier concentration is readily determined by this relationship. Of course, the semiconductor needs to be in equilibrium state and non-degenerate. Thank you for watching. Please continue to the next video in the playlist.